Today we're going to continue our discussion of the hydrogen atom from the last few videos. If you recall, we were able to sort of look at the simple Hamiltonian for a hydrogen atom and separate it into two Hamiltonians, one that only depended on the center of mass coordinate and one that depended on sort of the relative position of the proton that makes the nucleus and the electron. Um, this sort of led us down the path of how we're really going to approach this problem of solving our energy eigenvalues and our eigenfunctions. We really just are interested for the moment with this relative Hamiltonian and trying to determine what the energy eigenfunctions for that are. And we saw that the potential of the hydrogen atom is spherically symmetric, so we want to use the spherical coordinate system, and that essentially this wave function is going to be separable into a radial part and an angular part that depends on theta and phi. Today, we're going to continue looking down this, proceeding with this separation of variables type method. But we're going to quickly, before we do that, sort of recap a little bit of angular momentum to get us going with all that. So starting classically and with what angular momentum is, right? We define the angular momentum as just our cross product with the linear momentum, right? So if you remember, you have some coordinate system, and let's say we have some particle moving with some velocity, and it's at some position r. We take the cross product of those two vectors, r cross mp, uh, and that gives us the angular momentum of that particle about that origin. So if we do that and we want to calculate it, well, we can just do that just by taking the determinant of this, Rx, Ry, Rz, and the components of our, linear momentum, right? And this equals, when we do this cross product, we have the x component, which is y times z component of the momentum, minus c y component in the I hat direction, and then the other two components. Oops. C, X. And finally, the Z component of the angular momentum would be this one. Right, so immediately we've sort of sorted out what our components to the angular momentum would be. Knowing the position space representations of x of our position and our momentum operators, this means we can take our these components and write them in the position space representation, which would be just y d dz minus z d dy would be our Lx. And then similarly, we could get the components in position representation for the others, where the position variables are just those variables, and the momentum operators are just the negative IH bar partial derivative in that coordinate, or in that component. Knowing all this, we can actually, and this will be again, something we cover perhaps a bit more in the synchronous session, definitely on a homework assignment. This can actually give us all our commutator relations in quantum, right? For the quantum versions, we know that the commutator between that is IH bar, and similarly, it's going to be the same thing for Y and the other components as well. We can derive this using, this sort of component that we got classically, and the same way we've derived other components. And likewise, that also gives us the components, um, the commutator between the different angular momentum components being just IH bar LZ. And these should look pretty familiar, right? There's also cyclic permutations of these commutation relations, uh, IH bar LX, and then the third one would be this. And uh, these should look somewhat familiar if you think back to our commutation relations for our spin angular momentum, right? It's just another type of angular momentum, so that perhaps doesn't surprise us, but we get the same sort of analogous commutations when we're just looking at this uh, classical sort of orbital, we're going to call it angular momentum, due to, say, an electron in a certain orbit around a proton. We get the same commutations we get for that angular momentum that we get for sort of the intrinsic spin angular momentum that we discussed last semester. Similarly, just analogously, we remember that our spin operators had, you know, eigenvalue equations of the like this, and the z component of that spin operator was equal to that. So again, hopefully you remember all this. The orbital angular momentum, or the angular momentum we're looking at now, it again analogously is going to have the exact same thing, where the squared of the orbital of the angular momentum operator is going to have similar quantum numbers associated with it, and similar eigenvalues, and we'll actually derive these in an upcoming lecture. But for now, just pointing out how they're exactly, or very analogous to what we saw with the spin angular momentum from last semester, and the stuff we've sort of been using the whole time with the spin quantum number, where L is, the quantum number L is related to sort of the size or the magnitude of the angular momentum, and the sort, yeah, and ML is what we would call the orbit magnetic quantum number. It's more related to sort of the projection onto the z-axis. Um, so yeah, the magnitude of the z component. So we've got all these same sort of things. One big difference is that we'll see and we'll arrive is with this orbital angular momentum quantum number. It can only be integer values, 1, 2, 3, dot, dot, dot. And ML can go from negative L to negative L plus 1, dot, 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 all the way up through, minus 1 to L. So from negative L to L in integer steps, whereas when we were looking at the spin quantum number, that could potentially also be half integers, depending on what the intrinsic spin of that particle was. It could be half integers. So that's one sort of difference between the spin quantum numbers and the spin angular momentum that we were looking at last semester, and have been through most of our discussions, and the orbital angular momentum that we're discussing today. Just like, and again, just analogous to the spin operators and the spin angular momentum that we were able to present in matrix notation, and that we can do the same thing with our angular momentum operators. If we take, say, a system with an angular momentum value of L equals 1, we can write our the angular momentum operators in the angular momentum eigenbases are going to look a lot like what our spin 1 system had in terms of angular momentum operators. Lx, the x component would be h bar over root 2 times 0, 1, 0. And hopefully, if not immediately obvious, these sort of remind you or look somewhat familiar because we dealt with these last semester and have looked at them a few times. Positive I. And then finally, the L squared operator is just going to be 2 h bar squared and the identity, because the L squared commutes with all of these guys. So right, again, I'm just sort of recapping things and showing some analogies between this orbital angular momentum that we're looking at and the spin angular momentum we've done. The gist is, though, we're trying to solve this Hamiltonian in the position bases and that. So we're going to be concerned with what these operators are in the position bases, and we haven't really done any of that with the spin, because the spin's an intrinsic property of a particle in that, whereas the orbit or the orbital angular momentum is going to depend on the position and how that electron, I guess, is sort of orbiting, to for lack of a better word, that the proton or the nucleus of the atom. So what is that? Well, we saw above that we derived sort of our components of this angular momentum classically, and we saw that Lz was just, where are we up here? Just x, the y component of the momentum, minus y times the x component of the momentum. So it was x partial y minus y partial x, right? That was what our z component was, right? And we also know that in our spherical coordinate system, we have all those relations. X is equal to r sine theta cosine phi. Y is equal to r sine theta sine phi. Z is equal to r cosine phi. We also have r is equal to just the sum of the squares of all those components. And we can also figure out our angular components by doing some trig, y over x, and the last one, theta. A few ways you can do this, but let's do inverse cosine z over r x squared plus y squared plus z squared. So we have all these components, so we can actually figure out, we're using the spherical coordinate system, so we sort of want to convert this into the spherical coordinate system. And to do that, the tricky part, we can just sub in these values here, but we also have to somehow convert these derivatives into spherical coordinates. And to do that, we essentially just do sort of the chain rule. This is going to be d dr dr dy, and you have to do that for all the components. Theta d theta dy and d partial phi dy. And we can do all this. It's a bit of work. Maybe you'll assign it on a homework, and that is pretty tedious. But we can work through this. And what we get when all is said and done is we get our angular momentum operators in the position representation after all is said and done, and we end up with negative I h bar partial phi is our z component, and our L squared component is going to be negative h bar squared 1 over sine phi partial theta sine phi partial theta plus 1 over sine squared theta partial squared partial phi squared. So we can, oops, sorry about that, derive our, I'm having trouble drawing straight lines today. We can derive, we've sort of derived and come up with our angular momentum operators in position space. And this is actually going to be quite useful in our in solving that Schrodinger equation, actually, in solving our energy eigenvalue equation for the hydrogen atom. So continuing on with that, let's think back to what that sort of relative Hamiltonian we derived last video was. We get negative h bar over 2 times that effective mass, and then we had Laplacian and all that, which was 1 over r squared, partial r. Let's speed this up a bit. R squared partial r plus 1 over r squared sine theta partial theta sine theta partial theta plus 1 over r squared sine squared theta partial phi squared. And that was acting on our wave function that we're writing in spherical coordinates. They're operating on that times our potential operating on the same wave function, and the energy eigenvalue equation gave us the energy of that system times our, again, our wave function, eigenfunction in that coordinate system. So that is our Hamiltonian, and if we look at this, we can compare and see this part is quite similar to that part, right? You know, it's the exact same thing, except for it's got a 1 over r squared that we could factor out of this. So our Hamiltonian can actually be rewritten this way. 1 over r squared, partial r squared, r plus, oops, sorry about that. Minus 1 over h bar squared r squared L squared r theta phi plus that potential times our wave function equals E psi r theta phi. What this means is all this angular part, all this angular momentum, essentially what this means is that our Hamiltonian and our angular momentum operator are going to commute, right? If we throw in another L here, either front or before, it's not going to affect how it operates on this, all right? So we basically just got to the point where we know that our L squared operator commutes with the Hamiltonian, which we know means they share eigenstates, right? So we know that the eigenstates of our angular momentum squared operator give us the angular eigenstates of our our hydrogen atom, right? So remember, we have that wave function in spherical coordinates that we have sort of separated into a radial part and a angular part. The gist is these are going to be the eigenfunctions of our L squared operator and all that. And since we also know that that L squared operator commutes with our Z component operator, or actually any of the component operators, they're also going to be the eigenvalues of the L sub Z operator. So the gist is now we're going to attack those two operators and try to find their eigenvalues or eigenfunctions. We're going to use the same separation of variable techniques that we've kind of been going at. It's separation of variables all the way down to determine what these eigenfunctions are, and like we said earlier, ultimately put them all back together to get our full hydrogen atom wave functions. Let's find these functions, right? So we've got our Hamiltonian right here, and we know that we're writing our wave function using separation of variables as an r function that only depends on the radial component, and then the y that only depends on the angular component that, I'm just going to write as r times y to save space. But so what does this energy eigenequation end up looking like? Well, we can sort of just sort of substitute to see where we're going with this, but we have negative h bar squared over 2m times, well, if we substitute our y here, this L squared operator is independent of r. So it's only going to operate on the y, so the r can come right across to the other side. And likewise, these operators only operate on the r, so the y can come through the other side. So this ends up being y times 1 over r squared partial r times r squared partial r, capital R the function, times partial r, minus 1 over h bar squared r squared times that radial function times the L squared operating on our angular function, plus v of r acting on our wave function, r times y. That's going to equal our energy times our wave function, r times y. Now, we can bring now, this is one of the key parts of separation of variables, we can bring all the r terms to one side and all the angular terms to the other, and just with a little bit of algebra. And what this gets us to 1 over the radial function times partial r squared, r minus 2 mu r squared, e minus v of r, all acting on r squared. And that's going to equal, when you bring all the angular stuff to the other side, 1 over h bar squared, 1 over y, L squared acting on that y variable. So what we've got a parentheses there. What we've got is we've done a bunch of algebra in this step that I'm not going to spend more time doing here. Hopefully you can do it on your own and follow it. But we've got this side only depends on our r component, and this side only depends on our angular components theta and phi. Right? Now what this means is, if you think about it, this equation, this is true everywhere, right? And so we're free to change r, theta, and phi to whatever we want, and we want that, and this equation's true. So you can imagine moving just in the radial direction and changing r. This side isn't going to change. It's going to be constant. We haven't changed anything here. The r changing on this side has changed a lot. So what that's essentially saying is that both of these sides are equal to some constant. We're going to call that a right now, right? So we've now sort of broken down our Hamiltonian into the radial component and the angular component, and we've shown that rather than having one huge differential equation, we can essentially set this side equal to a constant and this side equal to a constant and solve them individually, and that's essentially how we're going to proceed. Those two equations essentially boil down to, the first one comes from the left-hand side, negative h bar squared 2 mu r squared, derivative of r with respect to r squared ddr, plus v of r plus a h bar squared over 2 mu r squared, all acting on our radial function, our function that only depends on r, and that's going to be equal to the energy times that radial function, right? So this, it's just algebra on this side of the equation here, equal to a, where a is just that, thus some constant we haven't defined yet or figured out what it is. So this is our first one of our differential equations that comes from that. The other one is the corresponding one for the other side, and it ends up being just L squared times that angular function. That's going to be equal to a squared h bar squared times our angular function again. And these two equations, essentially, the way this whole process is going to work is we're going to solve equation 2. That's going to determine our A. Then we're going to plug it back in here and solve equation 1, and so forth. We're actually going to repeat this sort of whole separation of variables process to solve this spherical harmonic term, or this angular term in this differential equation. Doing that, we essentially, we're just going to say that my angular term can be written as just a function that depends only on that polar angle theta, and one that depends only on that azimuthal angle phi. We know then that our L squared, well, we showed this earlier, that L squared operator is equal to 1 over sine theta partial theta sine theta partial theta, plus 1 over sine squared theta second partial phi squared. So if we take this and L squared operating on our y function is going to give us, let me rewrite this now with a little more space, L squared times y theta phi. If we make this sort of, if we separate this into those two functions and operate on them this way, we can see that this term is only operating on that phi function, and this term is only operating on that theta function. So again, we're going to do the same sort of thing and just proceed through this. And we're going to get two differential equations, one for theta and one that involves phi. So running through this, and maybe I'll speed this video up in post because no one wants to watch me just write equations. But this is going to be a squared h squared theta times phi, where L squared operating on this goes back to this equation here that we're trying to solve. So this is our differential equation that we're trying to solve. And again, this is only operating on our theta function. This is only really affecting our phi function. So we can bring them all through. And this, rather than bore you with me writing out the long equations again, ultimately we end up with 1 divided by our angular, or our function that only depends on the polar angle, sine theta. I'm going to have to rewrite this, being explicit with what our functions and not just to be clear, but our theta as a function of theta, sine of the variable theta, partial theta, sine theta, partial theta, our angular function theta, plus 1 over our azimuthal function phi, which is only a function of phi, sine squared theta, partial phi squared, acting on that azimuthal function phi. And this whole thing equals that constant A. And again, like we saw with the previous one, we've sort of separated terms into ones that depend on theta, ones that depend on phi. You do some algebra here, starting with multiplying everything by just sine squared phi, and we're going to cancel out a bunch of sine terms, bring it over here, and then do a bunch of algebra on that. And again, rather than you watch me do some pretty trivial algebra that just takes some time, we'll skip to the result. We end up with sine theta over our angular function partial theta sine theta partial theta of our polar function minus a sine squared theta. And that, if we bring all the azimuthal stuff to the other side, 1 over our azimuthal function times partial phi squared of our azimuthal function. And just like we saw again last time we did separation of variables, we've got all the theta stuff over here, all the phi stuff over here. And again, the same sort of reasoning. This equation we've got to is true for all theta and phi. So you can imagine going to a different polar angle, but staying at the same azimuthal angle. This has to be true. So if we change our theta and keep our phi constant, this side is changing a bunch and this side isn't, which means they both have to be equal to a constant, right? If changing the variable that is on the left-hand side doesn't affect the right-hand side and they're still equal, then this whole thing must be constant as a function of theta, and this likewise, this must be constant as a function of phi. So we set this whole thing equal to a second, a different constant, b, just some separation of variable constant we've yet to determine. And now we have two differential equations from this separation of variables thing. The first equation is just 1 over sine theta, the derivative with respect to theta of sine theta d theta, minus b 1 over sine squared theta, all acting on our polar function. It's going to be equal to negative a times that polar function. And our second equation is that azimuthal one, which is the second derivative with respect to that azimuthal angle of our azimuthal function, is going to be equal to negative b phi, our phi function. And again, we can solve this, and this is, we've sort of done separation of variables down to get our differential equations in this problem. I think this video is going to run long enough that we're going to stop here. Next video, we'll actually go through and start solving these, but we've going back to sort of the high level picture of this, we had our wave function for our energy eigenvalue equation, or energy eigenfunctions, and we did separation of variables on this that gave us that we wrote in terms of a radial component and a theta and phi component. And then looking at the differential equation, that separation of variables gave us for this spherical harmonics is what we'll end up calling it. But on this angular part, we did separation of variables on that and wrote that as a essentially a polar term and an azimuthal term. And that separation of variables gave us these differential equations. So each time we did sort of a separation of variables, we got one differential equation became two differential equations, but we added some separation of variable constant that we had to determine. So hopefully we can kind of follow this. The textbook has a nice little flow chart that goes into a lot more detail of the reasoning and the steps to sort of solving this. But the gist is, we're going to look at this differential equation, solve it. That's going to tell us, our azimuthal function and a lot about our b here. Then we're going to use that to, look at this differential equation. That's going to give us a lot of information and tell us about our a there. And then we'll go all the way back to that differential equation we have for the radial component. And that one, if you recall, actually involved the energy as well. So putting those all together, we'll be able to get to the root of this problem. If there are any questions, email me, bring them up in the synchronous session. We'll discuss this a lot more. And next video, we'll start actually going through these differential equations and solving them and moving forward with this. I will see you then.